Hello! Today we're going to learn about hashes, an especially useful Redis data structure. In this segment, I'll explain what hashes are, and I'll show you how to use them to model domain objects in an application. Hashes are collections of field value pairs and look a lot like a JSON object, a Java hash map, or a Python dictionary. Redis hashes are also mutable. We can add, change, increment, and remove field value pairs at any time, not just at the initial declaration. Hashes store field values as strings, which means that they are flat. There are no nested arrays or objects. Also, we do not need to predefine field names of Redis hashes, and as such, we can add and remove fields as needed. While Redis hashes are schemaless, you can still think of them as lightweight objects or as rows in a relational database table. To explore Redis hashes in practice, let's think about how we'd model a player in a fictional online role-playing game, Mages and Minotaurs. In a role-playing game, players live, die, and are reborn, and this cycle of life is reflected in health points, armor, abilities, and battles. We'll store this information in a hash, with every player getting their own hash instance. We'll update this player hash with new information, create temporary fields, and use built-in functionality to increment numerical values and update strings. Enter the player Artexius, the proud elven knight. For this first example, we'll create a hash starting off with the fields name, race, level, health points, and gold. To create this hash, we'll use the command HSET. The first argument to the HSET command is the key name we'll use to access the hash. In this case, it's player:42. Here we're using a common Redis key naming convention. We start with the word player to indicate what type of thing we're storing. We then follow with a colon and the ID of this player. The colon separates the various parts of the key name, going from least specific on the left to most specific on the right. After specifying the key, we add as many field value pairs as we want. When we run this command, Redis returns 5, indicating the number of fields saved to the hash. We've now created a Redis hash, our first player for the Mages and Minotaurs. Now let's see how to update and delete fields within a Redis hash. Imagine the player Artexius is having an epic battle with a wizard and received a thunderbolt spell to the head. In the game, he'll have a status of dazed. To reflect this game state in the Redis hash, we will add the field value pair status dazed to the player hash instance. Here again, we'll use the HSET command to add a new field value pair. So the command we'll run is HSET player:42 status dazed. What happens when our player no longer has the status of dazed? We'll want to remove the status field from the hash instance. To delete a field value pair from a Redis hash, we use the command hdel. The command is hdel player:42 status. Now the player:42 hash instance no longer has a dazed status, and Artexius lives to quest another day. Getting data from a hash is just as easy as setting it. Suppose we need to retrieve Artexius' level. For that, we'll need to use the HGET command. The command is HGET player:42 and then the field we want, level. To get all of the fields and values from a Redis hash, use the HGET_all command. We'll run HGET_all player:42. This will return all fields and values contained within the hash. Now, in many role-playing games, players receive gold after completing objectives or defeating enemies. We'll need to be able to increase the amount of gold a player has whenever this occurs. Guess what? There's a command for that. It's called HINCRBY, and it increments the value of a particular hash field. We enter HINCRBY player:42 gold and the increment value. Let's increment the value assigned to the gold field by 120. Okay, finally, let's talk about the performance characteristics of these hash commands. Most hash commands are O of 1, which means they will always perform a task in a constant amount of time, regardless of the size of the hash. Constant time commands are as efficient as it gets. The HGET_all command is O of n, with n being the number of fields within a hash. This means that the amount of time for the task to complete is dependent on how many fields it has to retrieve. In this case, the n of O of n is the number of fields that the hash contains. HGET_all is practical for relatively small hashes, such as our player hash. For hashes containing thousands of fields or more, it's usually most efficient to select the exact fields you want using HGET rather than retrieving all of the data with HGET-all, or HSCAN. Okay, let's review. We've just explored how we can use Redis hashes to represent player objects in an online role-playing game. We've learned that Redis hashes exist as collections of field value pairs. We created and updated hashes using HSET. We retrieve data with HGET and HGET-all. Fields can be deleted with HDEL. Lastly, we incremented numerical values using HINCRBY. As useful as hashes are, they aren't the be-all and end-all for object storage in Redis. If you're dealing with nested structures or JSON, check out Redis Json. Redis Json is a Redis module that implements the JSON data interchange standard as a native data type. It implements efficient storage, update, and retrieval of JSON data in Redis. To learn more about Redis hashes, check our free online course, Introduction to Redis Data Structures. It's part of Redis University, our online learning platform for all things Redis. Thank you for joining me in designing mages and minotaurs. I hope to go on another quest with you again soon.